Good afternoon, everyone. We welcome Professor Gillian Folger to come our university today here. Now, first, we welcome you to come to our Forum of the Future Ocean today. I'm Zhou Xiajiang, the supervisor of the Future Ocean University of China. It's our great honor to invite Professor Folger Gillian to give us a talk here. At the beginning, I would like to make a brief introduction of Professor Folger. Professor Folger is an academician of the Atlantic Academy of Sciences and also the professor of Durham University, UK, and the visiting professor of Ocean University of China. Her research focuses on the origins of hotspots and flight bosols, in particular the existence or not of the mantle blooms. She is a specialist in the North Atlantic Eugenics province, including the structure, tectonics, and dynamics of Iceland, volcanic and geothermal seismicity, and geothermal exploration. The topic of her presentation today is Iceland a continental large igneous province? So now let's welcome Professor Folger to give us a talk here. Let's welcome. Yeah. It's your turn.
Okay, wonderful. And I have a choice of two here. Are they both the same? So I'm going to talk to you about a kind of quite an advanced theory here, and that is whether Iceland is a continental large igneous province. So the question is Iceland underlain by oceanic crust, which is just basalt, or is it underlain by continental material? This is something that the scientists who are at the limits of research are asking at the moment. And here in China, I'm working with OUC and also China University of Geosciences in Wuhan to conduct experiments to test this hypothesis. Okay. So to start with, just the regional picture. Here is Iceland. So this is the Arctic Ocean, and I understand from colleagues that there is a Chinese research vessel which once a year goes to the Arctic Ocean and does research there. Well, if the vessel continued sailing until it came into the Northeast Atlantic, it would come to this region here, which is the area that I'm studying. In this region, we have a large landmass here. So it's an unusual ocean because there's a big landmass where we can do land experiments. So this is quite unusual. In the Pacific Ocean, for example, there is no such large landmass. Iceland is 500 kilometers from west to east. This is the simple situation that scientists have sort of assumed for many years. It's assumed this is the spreading ridge, which is fairly normal spreading ridge. I'll show you the magnetic anomalies soon. And this is a fairly normal spreading ridge too. The crust is about 8 kilometers thick here, 8 kilometers. Here it's about 8 kilometers thick. And the magnetic stripes are quite normal on either side. But Iceland is completely unusual. You know, there's no other place like Iceland in the world. And scientists often assume when they're just maybe teaching junior students, I think sometimes the professors don't give students enough respect and they give them a very simple picture. I think students are smart enough to know things are not simple. But they'll just say, oh, yes, the spreading plate boundary just goes through Iceland like that. But the situation is much more complicated. When I graduated as a master's student, I got a job in Iceland and I worked there for 7 years. And I came to know all the inside stuff, what was not published, and things that didn't fit, and things that usually you don't hear. So I always knew that this was too simple a picture. So I'll start by describing how the Northeast Atlantic formed. So this is the situation 54 million years ago. It's a young ocean. It's only approximately 50 million years old. And this was the situation there. And you can see that this is Britain. This is where I live, just here. This is the little bit further north, this one here. So this is where Harry Potter movies were made. And this is Norway and Sweden and Greenland. And you can see that before the ocean opened, there was a tremendous lot of continental crust, which is now beneath the surface of the ocean. The North Sea, the Greenland, the Norway Sea, and so forth. And this is the line where the spreading ridge started. And these red areas are seaward dipping reflectors. So when we look at the North Atlantic, we tend to think, oh, this is a big area of oceanic crust. But a huge amount of it is continental. And the question really is how much? So first of all, this spreading ridge developed. And a little later, this one formed. And this one started here, and it propagated south over 2 million years. In my opinion, not everyone agrees, but in my opinion, this area here, the ridges did not join up. There is an orogenic front across here. An orogenic front runs across here, and it ran down here and into northern England. And I think these ridges could not break across that structure. So these are the magnetic anomalies. And as you can see, we have the spreading ridge here. And we have very regular anomalies on either side. So this is quite clear. Many seismic experiments have been done, and clearly it's oceanic crust, just a few kilometers thick. And the same to the north, as I said, very clear oceanic anomalies. But on either side of Iceland, it's very rough, very unclear, very difficult. You know, you could say, oh, you know, I'd like to trace this anomaly across, this one maybe, but, you know, it gets very difficult and it's not at all clear. In fact, I would say that these anomalies look more like these anomalies here. You know, maybe you can say, okay, there's a linear thing here, but it doesn't look like this, and it doesn't look like that. So I would say, in my model, this is continental. But of course, you can have a model, but you have to then do a lot of work to show that this is supported by the data. So this slide shows the currently active extensional zones, and in blue, the extinct ones. South of Iceland, we have one currently active zone, and there's only been one. This active zone here, it's the same one as formed at the beginning that I showed you on a previous slide. In the north, this is the original ridge that propagated south. This is now extinct. Instead, it stopped becoming active, and a new one formed here. So presently we have one here. So this we can be sure of. In the Iceland region, we have many rift zones like this. And the width of the volcanically active zone is about 400 kilometers. So the volcanically active zone to the south and the north, this is just the mid-ocean ridge. So this is 3, 4, 5 kilometers wide. But in Iceland, it's 400 kilometers. So I think this is an important clue. Also, in this region, we see many extinct ones. So these were active once, but now they're no longer active. The same over here. So it looks as though the Iceland region, there were probably always two rifts. And as the ocean widened, these rifts traveled out, became extinct, and new ones formed in the middle. So we have a similar thing on the East Pacific Rise. Maybe this is an area you're more familiar with. So this is an example of, in this case, two ridges that overlap. So the Icelandic ones don't overlap, but these overlap. And as the spreading continues and it opens, these become extinct and new ones form. So this is the model that I have in mind. And this is the result after some millions of years. There's a kind of messy zone here without proper anomalies crossing them. Okay, another piece of information we have is this so-called land bridge. It's been called the Thulian land bridge. In old English historical stories and myth, there was a land called Ultima Thule, and this land was supposed to lie far to the north, and this was the land where dragons lived and other magical beings. So this geological feature has been called the Thulean route or the Thulean land bridge. And this is known, this is not my crazy idea, this is fact, that as the Atlantic Ocean opened, for the first 40 million years, as the ocean opened until it became 1,000 kilometers wide, there was a bridge of land that crossed it. So this is a very, very strange thing. Where else can you see a wide ocean with a bridge of land across it? So this is known from plant fossils, and also because the time at which water in this ocean flowed south, this can also be dated from sediments. So we have these two pieces of information that this ocean was only connected to this ocean 10 million years ago. So 10 million years ago, it was just continuous land from Greenland across here to Europe. So this part has now subsided beneath the ocean, and this part subsided too. So Iceland is not really a kind of special thing. It's just the one remaining part which is still above sea level. It was once a long structure that connected both continents, not a special little nicely round island. This is a close-up of Iceland itself. So when I worked in Iceland, I lived in the capital city, Reykjavik, here. Then I thought I should buy a house, but the cost of houses was too expensive. So I bought a house in a little village here. And if you've seen the news recently, you'll know that there have been volcanic eruptions. Iceland's a very famous place now. And these volcanic eruptions are here. So just this last summer, I was in Iceland collecting rocks, and volcanic eruption started, and all the guys with me said, "Oh, great! Whoa, a volcanic eruption! Oh, I've never seen a volcanic eruption. Let's all go and see the volcanic eruption." And there's me thinking, "Oh, distraction. I went to Iceland with this group to collect rocks. Now everybody wants to look at the eruption, but we were able to finish the rock collection and also see the volcanic eruption. Okay, but it's quite a problem because there's a village here, a fishing village, and the eruption started here. So the activity, it's threatening to cut the road. And the international airport is here. So if this volcanic activity extended up here, it could cut the international airport off from Reykjavik. So this would be a huge problem. Anyway, the point of this is to show you that the volcanic zone, it extends from here to here. So this pink here, the pink areas is the region of lava, which is younger than 10,000 years. So the pink area is covered with lavas which formed as the Chinese culture developed. The pink areas, their lavas approximately the same age as the development of Chinese culture from thousands of years ago to the present time. The green is a little bit older. The green is up to 0.7 million years. So, hang on a minute. Maybe that's okay. So I think this is 0.7 million years. So this is measured because this is the present magnetic polarity, the present normal magnetic polarity. This goes back to 700,000 years ago. And this is the green areas. The blue areas, the oldest rocks are here. This is fairly old stuff, about 13 million years. And this over here is about 17 million years. So these are the oldest regions, and it becomes younger as you go in. So clearly, you can see that this is not what we expect for a normal mid-ocean ridge. So already, I'm sure I've convinced everyone in the audience, at least, excuse me, I'm sure I've convinced you all that the simple model, often shown to undergraduates, is too simplistic. It's not like that. This is quite an interesting exercise, I think. So the rate at which the ridges are spreading here, this one here, this one here, is 2 centimeters per year. So it's very slow. So if we take Iceland and we close it up at 2 centimeters per year, then this is the present situation with the old extinct rifts and the currently active ones. This is the situation at 2 million years, 7 million years, and 15 million years. So at 15 million years, the only Icelandic rock that was there is this to the far east, the very eastern and the very western. Everything else that we see on the surface formed younger than 15 million years. So we know then that this rift was active here and this rift was active here. But if you close up at this rate, 2 centimeters per year, then still this rift and this rift are still separated by, well, this is 50 kilometers. So this is 50 kilometers approximately, maybe this is 100 kilometers. So sometimes people say, oh, the situation in Iceland is really quite simple and it's just the ridges are jumping about. But you cannot explain the width of Iceland with this model. There has to be older stuff underneath. This stuff here, this has to be older than anything we see on the surface. So to begin with, these observations require, there's no other way of explaining them, they require that there must be some older rock underneath Iceland that's covered with younger lavas. I would say this could be called a microplate. So that's very interesting in the context of the new initiative here at OUC to develop a microplate institution, microplate group, which is what we're doing upstairs on floor 7. So this is one possibility to explain this older block that we can't see. Maybe this is the northern ridge and this the southern one. And if when they formed, they're offset by, say, 50 kilometers, then it must look like this. And as this is extended and this is extended, there must be a piece of continent trapped in the middle. So the previous slide where I closed Iceland up, these observations require an older block there, but they do not require continental block. This is one possibility. Okay? So it's very important in science to try to distinguish between what has to be, you know, what your data show has to be, and what is just one possibility. We have, of course, done a great deal of geophysics, and this shows seismic work that's been done. So the crust underneath Iceland is up to 40 kilometers thick. And we have the upper crust here, which is approximately 6 kilometers, 8 kilometers thick, so on. And then we have the lower crust here, which is approximately 20 kilometers thick, or in some places 30 kilometers thick. So the whole crust can be 30 kilometers thick, or it can be 40 kilometers thick. And this slide shows the map view. So this red is 40 kilometer thick crust. This purple is 20 kilometer thick. So there seems to be a thick piece in the middle. So again, it's possible that this is a continental block, but it could also be an oceanic microplate which has been overrun with young lavas. So we're in a very interesting situation here of knowing that there's stuff underneath the very young surface lavas, and we don't really know what it is. This is what the discussion is all about. It has been done to plot the thickness of the crust against the height of the land surface. So if the crust is very thick, the land should stand at a high elevation. In Iceland, this has been used to calculate the density of the lower crust. And the density of the lower crust is very close to mantle density, which is a big puzzle. So the density contrast, the difference in density between the mantle and the lower crust is about 150 kilograms per cubic meter. If the lower crust was gabbro, the lower crust was oceanic, this should be about 300. So this is another kind of fishy thing. And again, what is behind this slide is very, very technical. It's petrological estimates of the temperature of the source from various, lavas. So people collect samples of the lavas on the surface, and they use petrological methods to calculate the temperature of the original source. And without going into a lot of detail, this is the subject of one very huge paper. the temperature underneath Iceland is not very high. So this is mid-ocean ridge basalt temperatures here, and Iceland is maybe 75 degrees warmer, but not a lot warmer. We also have seismic data, which can give us the temperature of the lower crust. So the lower crust under Iceland is actually quite cold. It's no more than maximum 900 degrees. So we think the temperature of the convecting mantle, which feeds mid-ocean ridges, we think that is about 1,350. But the lower crust under Iceland is only about 900, and it contains no melt. And we know this because seismic shear waves pass freely through it without attenuation. So everything, a colleague, an American colleague, published a paper which he called "Cold Crust at a Hot Spot." So these are the problems that I've lived with all my career, needing to explain these in a way which seems right to me, and this has been quite difficult. And I think just a few years ago, just 5 years ago, I think we finally found a theory that can explain all these strange observations. And I think this is continental crust under Iceland, but this still remains to be tested. I don't have a clock here, so I don't know. Oh, wonderful. Thank you. I don't want to bore you for too long. Okay. So now I'm going to explain the theory to you that my colleagues and I are working on testing. So we're quite a big group. When we published this theory, I think there were 19 authors on the paper. So there are a lot of people who think this is a interesting theory, maybe surprising, but there's a lot of support for it, and it needs to be tested, and that is what we're trying to do. Okay, so here we have Greenland. So this is where I get involved with geologists who are interested in continental rocks, in particular very old continental rocks. So you will perhaps have noticed that in my talk here, I've talked about many different subjects. Officially, I'm an earthquake seismologist, but I have to get to understand isostasy, petrology, heat flow matters, explosion seismology, gravity, magnetics. And just when I think I've kind of got some understanding of all these different things, all of a sudden I have to get to understand Precambrian continental geology. So I'm very lucky that I have many very able and willing colleagues around me who can fill in all the big holes in my understanding. But Greenland is a very old bit of continent. There's a lot of Proterozoic rocks here, craton here, and it's cut by many very old sutures. So these are Proterozoic sutures. And we have a suture zone down here, which is younger. This one is only 400 million years old. So this one is Paleozoic. These are Proterozoic. Okay. So this is a simplified diagram showing where the main sutures are. These are the old Proterozoic sutures. Yeah. And this is the 400 million year old suture. This is just Paleozoic. So this shows the ocean opened. But if we put the ocean back together again, this edge of the suture would run through Britain. So you have to imagine these continents put back together again. And this is the eastern edge of the suture, and this is the western edge. So this ridge here with Iceland, this formed along this orogenic front. So if we were to draw a cross section across here before the ocean opened, supposing we drew a cross section across here, okay, this is what we think you would see. So this can be the north, and this can be the south. So of course this is the Himalaya orogeny, and this is just a kind of cartoon. But basically, it's suggesting that we have very thick crust here and a lot of slab material underneath. So we think that when the Atlantic came to open, that one ridge came down here from the north and it stopped here, and it could not break this very strong cross structure. The other one came from the south northwards and stopped here. So it was this region here which it was very difficult to break up, and we think it still has not broken up. There is some evidence for this. So a colleague of mine put seismic stations out in Greenland. So this is East Greenland, and there are also seismic stations in the north of Britain. And this colleague, he proposed that this structure here is the moho, and that this is the remains of the slab in the mantle. This is where he says he interprets this as being a slab. And in Britain, we also see a similar structure here, which my colleague, Christian Schiffer, he was a postdoc with me, he interprets this. In fact, he'd done this work before he came to Durham, and he applied to come to Durham because he had this idea, and he felt that his ideas would fit with the ideas in my group. So, very good. So this is what we think happened when the Atlantic opened. Here is the suture. It's the western front and the eastern front. So a colleague whose name is Peterson, he has drawn this this part of the suture front green. And when the continent opened up, when the ocean opened up and the continent broke, he's proposed that this very strong belt of rocks just simply stretched. So he went on to do a numerical simulation. So in this simulation, this red is the crust, the green is the mantle lithosphere, and this purple stuff, this is the extra slab thickness underneath the orogenic belt. So he ran this model for, okay, you can see how many million years here. So I'll tell you when it's 50 million years, it is 50 million years now. Okay, so then he continues it on for 90 million years. So where we stand today, at 50 million years, this is halfway through this simulation. So you can see that this is just the top part. You can see that at 50 million years and even up to about 70 million years, the crustal part is intact. The crustal part has not yet broken. You can see this rather nice structures forming with large faults and so on. And what he found was that when this thickened thing drops off, so you start off with extra thick crust. So the crust stretches, this eclogitic thickness at the bottom drops off, the asthenosphere rises up, and it heats up the crust and makes it easy for the crust to stretch. So in American, we would say it's stretching like taffy Taffy is that candy, which you can stretch like this. I don't know if you have some food in China, which would also be a good. Do you have some food which stretches? What would that be? Noodles. Okay. Probably many different recipes. So this does not prove that this is correct, okay, for the benefit of the students. What we did here was a numerical model using the best possible parameters, reasonable temperature for the mantle, reasonable thickness of the crust, and so on. And we ran this model to see if our theory was possible. So this model shows that our theory is theoretically possible, but it doesn't show that it's true. Okay? It's just a test. It's like when you go to the doctor and you say, "Oh, terrible headache," and so the doctor takes some measurements, takes a scan, and takes blood pressure and so on. And the doctor might say, "Well, you could have this problem or this or this or this." So all these are possible, but he's not proven anything. So the doctor might say, you could have these 4 things wrong with you. So I have to do another test to check if it's this one. Okay. And if that test is negative, he says, okay, we have 3 more possibilities. This is how we work in science. We eliminate different possibilities until hopefully we just have one left. So, so here we've basically shown that this is possible. We've shown that this maybe is one of the 4, if you like. We compared it with seismic tomography. So this is one fairly recent seismic tomography result. I could show you 5 or 6 others. And this one shows that there's a very strong seismic anomaly in the upper, 300 kilometers or so. And it shows that there's some sort of weak anomaly down here, which to me, is quite possible. This can be the topmost body, and this could be, because when this stuff drops off like this, whoosh, it sets up a kind of symmetrical convection current. So, it's kind of nice if things fit, but you have to remind yourself always that this is not proof of anything. So this is the structure we think for this whole ridge from Greenland to Europe. We think that basically the whole thing is underlain by stretched, hyperextended. We think this is a hyperextended volcanic passive margin. So we think the continental crust is still stretching, and we think we have SDRs here, seaward dipping reflectors on the passive margins, and in Iceland we just have a lava cap with some of this continental material underneath. So the volcanic activity that we see in Iceland, this may be the only place on Earth where we're seeing SDRs forming, seaward dipping reflectors forming. So we're pushing this model because we feel it answers all these questions, which often are not mentioned in scientific papers. Much of the stuff published about this area just kind of doesn't mention the problems that I've told you about. It just sort of ignores them. But the crust has a huge thickness, and this cannot be explained by just even high temperature. You would need impossibly high temperature to build such a thickness of basalt. It would explain this strange observation that there has to be older crust under Iceland. It would explain the high density of Icelandic lower crust because these densities fit continental model. It would explain the magma volume. So even if you take a mantle plume or something like this with high temperature, it's virtually impossible to produce this huge 40-kilometer thickness of basalt. You would need an enormous temperature. We would probably see komatiites, this kind of thing, in the rocks. and we do not even find pickrite glass. The magnesium number of the glasses doesn't go above 10 or 11, something like this. You know, it doesn't go to 15. It's not picritic. So there's a lack of evidence in the basaltic rocks for the temperatures high enough to produce 40 kilometers of magma. And it would also explain this, because you know, the continent would stand higher than the surrounding sea basins. So we have a theory, and we're busy going out and testing it. And from memory, we wrote in the paper that there are 4, magic number today, 4 obvious ways in which we could try to test this theory. One is looking for ancient zircons. So these could be preserved in the lavas. The other was doing an electrical survey of Iceland. Another one was, let me think, what was it? Oh yes, doing a very deep seismic reflection experiment from Greenland to Europe. Okay, this might cost 10 million euros, so we have to do the inexpensive things first. And the other one would be a deep drill hole. So if anybody is interested in finding maybe 100 million euros or 1 billion RMB, we could drill a drill hole in Iceland down to 6, 7, 8 kilometers, see if we find continental crust. So we've started on this. This is the last part of my talk. We had these great plans, and then the pandemic started. So this field work was postponed and postponed and postponed. But this last summer, 2023, finally we had the money, the people, the travel visas, the equipment, everything came into place. A lot of people worked very hard. We were going to do this in 2022, but then it was not possible. There was some surge of COVID, you know, and the field workers could not get visas. That had to be cancelled. But finally, 2023, we managed. And this heroic group, these guys are so tough. Okay, so working in Iceland is horrible. It's just horrible. You know, the weather is terrible. It's freezing cold. It's wet. No hotels, no restaurants. They had to bring their own food. The Icelandic food is terrible, so if there were no restaurants, maybe this is a good thing. You know, rice, no rice, okay. Fish, potatoes, that's it. Very expensive. So we hired a big sort of caravan for them, and this caravan was driven to the field area, and they lived in this caravan, and then they discovered there was no hot water in the caravan, so this was unpopular. Iceland, the land of geothermal energy, no hot water. But these guys, they solved all these problems and came back, and they were even smiling at the end of it. So this is what they did, and this is what they measured. So these dots, these are the planned sites, and they did all the green ones last summer. So the road goes around the coast here. And there's one town here with approximately, I think, 10,000 people living there. Just a small village, really. And the rest is just farmhouses. And in many places, no roads here. There's no roads here. So this was very challenging field work. So I really gave them a big thank you at the end for doing this. And this is a 3-year plan. So next year, they'll probably do this lot here. And then the final year, they do this lot here. So this is where most Icelandic people live around here. So this is quite easy. But these areas are very challenging. Anyway, that was one thing that happened this year. And the other project that got going was collecting zircons. So this is my group here. This is just to prove that I can go into the field too. This guy's from Peking University. This guy's from Canada. This guy's from the United States, and this guy from the UK. So this is what we sampled. All of these purple points. We had 2 field groups. So we had a big heavy vehicle, two vehicles, one for each group. And my group went to all these places and took zircon samples. The other group went around here, and then we met up here. So to do these interior ones, this is a very dangerous area, very remote. It's very easy to get the car stuck. You have to drive across rivers. And on one occasion, the car was stuck, and I had to come along with my car and drag them out of the river. So the way I planned it was that when I'd done these and the other group had done these, we met here at point 17, and then we did these dangerous points as 2 vehicles, because if one vehicle gets stuck, then the other can pull you out. So very important to not kill students, because we need them to analyze the samples afterwards. So we're now busy processing these samples and going out into the future. So thank you for your attention.
Okay, thanks. Thanks, Jillian. Very interesting talk. You know, there are more than 16 listeners online listen your talk. So you are fantastic. Thank you. So anybody have questions? Questions? Okay.
Thank you, Jillian. Nice talk. And I'm curious why you treat the Iceland possible basement of Iceland and special green terrain in your figure, because the whole paleo collision zone is a huge zone. So the Iceland basement just part of the great collision zone. So
are you referring to one particular slide?
Yeah. Yeah. This one. No. Next one, please. Next. Yeah, this one. So the Caledonia collision zone is big, and it's so the green terrain here is come from where? Why you?
So this is the edge of it. So up here, the spreading ridge formed along the suture, parallel to it. So it was forming along. It wasn't until it got here that it tried to cross over this orogenic front. In fact, I think Professor Liu could sort of talk more about the internal structures of orogenic belts. But I think it's easy to form a new structure along the origin, but to cut across the frontal zone where the final collapse, final slab went down, I think this is difficult.
But we think that the former collision zone are the weak zone, which is easier to be separated. So you just show us that this zone is just the collision zone with thick crust, and maybe the remainder archaeologic oceanic slab beneath. So I don't understand why they are difficult to separate it.
Right. So don't you think if you have a structure like this, it may be easy to separate it like this, but to cut across and separate these two, I think that must be mechanically more difficult.
Okay.
This is the thing. I think if you have, well, maybe noodles are not a good example, but if you have something which has a fabric in this direction, it's probably easy to part it like this, especially if you propagate a rift and you just tear it apart. But to go across the trend, I think that must be mechanically more difficult. This is our idea.
Okay. I have another question. So, from the geochemical perspective, the Iceland basalt is different to the normal mob. So, what's your opinion on this kind of a difference? They have a shallow orange, just like the other normal mob, or
Well, I'm not a petrologist, but I think this different geochemistry, maybe it's partly because the basalts are coming from the asthenosphere and they're traveling up through continental crust. And so I'm still working on this, but I can imagine the very first material, if it came up through continental crust, you would see a very big continental signature. But maybe it would then develop a channel. So then you're getting mid-ocean ridge type basalt coming straight up. And a lot of the rocks in Iceland, they look very similar to mid-ocean ridge basalt. So one way I'm trying to kind of, I'm like a blind woman feeling in the dark to find a way forward here. But one thing I'm doing is I'm working with South African colleagues. So I'm going to go to South Africa in August next year, because they have many large igneous provinces which we know sit on continental crust. And we know that this stuff has come up through continental crust. So I want to compare Icelandic lavas with, for example, the Karoo volcanics from South Africa to see if something can be learned from comparing them. And in fact, maybe there are also examples from China, for example, the Omishan large igneous province. We know this is formed on continental crust. So how about comparing that with Iceland, seeing if there's some similarities? Maybe there's somebody in the audience who could comment on that.
thank you.
Okay. Does anybody have questions? Okay, Jillian, I have a question about the Jiff Ridge. You have said that the Jiff Ridge is above the seafloor until 10 million years. So I wonder if the ridge influence the oceanic circulation.
Yes, it
Yeah,
did.
because we know that especially for Atlantic Ocean, the oceanic circulation is meridional. It's from the north to the south and then come back. If there is a ridge from the west to the east, it will be cut.
Yes,
Yeah.
yes, exactly. This I think I maybe mentioned that.
Yeah, here.
Yeah. So the
Oh, maybe there is another.
water from this basin
Yeah.
was isolated from this basin until 10 million years ago. And people who have studied the sediments here, they say that they can detect that water from here flowed into here about 10 million years ago. So this is when this bridge got broken.
Okay, so there are no exchange of the water until 10 million years.
Yeah.
Okay. Okay. Does anybody have questions?
Hi, Judy. I just want to show this map. What's your opinion about the V-shape Reykjanes Ridge?
I'm sorry?
Is it the V-shape Reykjanes Ridge? The mid-ocean ridge, yeah. If there is no mantle plume, how do you explain the V-shape the narrow to the south.
Narrow to the wide.
Yeah, narrow to the south.
This is a very interesting ridge because
Yeah.
it's made of ridge migrators. So it looks as though, whoops, sorry. This ridge is not just a straight ridge like this, but it's formed by many propagators. So there are many propagators. There are many propagators which propagate south, and this one retreats. And this has happened many times. Every time there's a ridge jump in Iceland, the Reykjanes ridge sort of migrates to another position and sends a propagator down. So the whole Reykjanes ridge is migrating to the east. So this is a little bit like the East Pacific Rise. So I think this would explain the unusual bathymetry here in the way that you described. But the crust under here is sort of more or less just, I think it may be 10 kilometers thick here, 8 kilometers thick here. So this ridge is a little bit complicated, but it's not that much different from a normal mid-ocean ridge, whatever that is. It's there isn't really anything much to explain except that it's tectonically unstable and therefore it keeps jumping and propagating. So with this plume hypothesis, you have to ask yourself, what is it we need to explain? So personally, I think everything can be explained by this continental model. I don't think we need a plume or high temperatures or big magma flux, because especially if the lower crust under Iceland is continental, we only have 6 or 8 kilometers of basaltic upper crust, and that's just the normal ridge amount. So I know it sounds sort of pretty crazy because everybody thinks, oh, Iceland volcanoes, oh, lots of magma, and so there must be something going on there. But when you actually look at the detail, the need for a plume sort of disappears.
In the Mandel plume opinion, they think that to the north, there are some geochemical signal, maybe from the deep mantle. I'm not sure.
Well, some colleagues argue this, yes. Other colleagues argue this can be explained by just shallow processes. And there are sort of complicated arguments on both sides. And that's very good, because if there's some disagreement and different points of view, then we have some challenge to address. So I like to meet colleagues who have a different point of view and disagree with me, because we have something to talk about then. Science is no good if everyone agrees, because then we make no progress. But yes, you're right. In particular, colleagues point to the isotope ratio of helium-3 to helium-4. And there's an argument that this comes from the deep mantle. And other colleagues say that, no, this can be trapped in old olivine grains. So they say that if you have old olivines which have great age, and they trapped helium in them from the very early Earth, then this helium can have a very high 3-to-4 ratio. And this is what we observe in Iceland. And people have said, if you have a high ratio of 3-to-4, then this must come from the deep mantle. And then there's this olivine idea. So this is another reason, actually, thank you for pointing this out, because if our search for zircons does show that there's very old Greenlandic crust from underneath there, then there's a source for this old helium signature. Good idea.
Jilin, I have a question. Please forward your slide. Go through. You listed some items to to describe the property of this Iceland underground geophysical data. Yeah, here. Yeah, this one. The three items you said the high density of island arc. If there is a continental below the Iceland, it should be because the continental density should be lower than the mantle or basalt.
Well,
Why here is high density?
Yeah. I mean, it's high relative to the mantle, but you know, if this was basalt, if this was gabbro, the density would be lower.
I think if there's some continental crust, it should be lower density with more acid rocks.
I see what you mean. Yeah, we think this is continental lower crust, not continental upper
not
crust.
the upper crust. Okay, thank you.
Does students have questions? Students? Okay, thanks, Jillian. Very good talk. Thank you. Okay, let's thank Jillian again. Yeah, very good talk. Yeah. Okay, thanks everyone to come here. Yeah, thank you.